we're going to discuss, we're going to go over an example. Meanwhile, if you have any question, please do ask. So let's assume that we have a uniform plane wave shown represented like this. And once you see this wave, actually the first thing that we may go after is to look, we can learn that the polarization of this wave is along the x-axis, okay? Which means that the electric field is pointing along the x-axis, but this is not the propagation. Okay, the propagation, it will be shown in the propagator. So we have a lossless medium, and in this lossless medium, we have epsilon r is equal to 4, mu r is equal to 1, and conductivity is 0. And the propagation is along the z-axis. So given these parameters, we can show the following. So here we have the x-axis. This is the y, and this is the z. Now, the electric field itself, it's pointing in this direction. So this is the ex. But the propagation of the wave, apparently, it's going to travel along the z. So here we have a k vector. Okay? And then this propagation, it will be such that it might represent itself or propagate like this. So electric field, it has a maximum, then it decreases, it becomes a negative value, negative maximum. So this is going to be the propagation of the electric field. At the same time, since this is a composite wave, the magnetic field H at this instant, it should be something like this, okay? Now, this is the XYZ representation of the motion. Now, let's assume also that F is 100 megahertz. Okay, so let's assume these given parameters for this wave. So we are given a frequency of 100 megahertz. We have the magnitude of the electric field, which is 10 to the power minus 4 volt per meter. And this amplitude, it is, let's say, at t equal to 0, at z equal to 1/8. Okay, so apparently we may modify a little bit this figure. So this is going to be the x-axis, and here the magnitude is somewhere here, and this is z1/8. So the maximum value, it is, we get it like this, and the question is, let's write, find E. Okay, so this is the question, which means that find the expression of electric field as a function of distance and the time at any instant. Now, the first thing that we have to write down, well, we have to first of all look at the given parameters. Now, this is the relative permittivity. Relative permittivity, ER equal to 4. Let's not forget that the permittivity is always equal to ER times E0. Okay, where E0 is the permittivity for vacuum. ER is equal to 4. Okay, so this means that at least this is some material which has a different permittivity. But also, let's remember that mu is equal to mu r times mu 0. So if mu r is equal to 1, this means that this medium is non-magnetic. Okay? So this is like vacuum. Vacuum is not magnetic. Now imagine for a moment that mu would be equal to 1.1 times mu 0. What would this mean? This would mean that this medium is magnetic. Okay? So when the moment that mu is different from 1, we have a different situation. But now forget this. From this one, we just learned the following: not magnetic. Okay, so this ER is equal to 4, conductivity is 0, this means that it's a lossless medium. The wave is propagating along the Z direction, as shown as given here. The frequency is 100 megahertz, and this 100 megahertz, it can help us to find important parameters. So let's continue. Let's say that K, the propagation vector, is equal, this is an essential identity. K is equal to the angular frequency times mu times the permittivity. And this is equal to the 2 pi f, okay, times mu r times mu 0. Okay, epsilon r times epsilon 0. Okay, so we just rewrite this one because we have these relationships here, and then this is then equal to 2 pi f. This is equal to 2 pi times the frequency. Frequency is 10 to the power 2 times megahertz. Megahertz is 10 to the power 6. Okay. This is 10 to the power 6. If you have anything which is not clear, please comment me. So this is 2 pi f, and then in this expression, let's write this here, 2 pi f times mu 0, epsilon 0, and this is mu r, epsilon r. We are good here, right? But we know that the square root of mu 0 epsilon 0 is 1 over c squared, so it is related to the speed of light. So what we can do here, you just erase this completely, and we divide here by the speed of light here. Which means that here, 2 pi f divided by the 3 times 10 to the power 8, which is the speed of light in vacuum, times mu r epsilon r. Here we get square root of 4 is equal to 2. So this is what we get, and then these cancel out, and we are left with 4 pi over 3. So we found the K, which means that this is 4 pi over 3 with a unit of radian per meter. So each meter, the phase, faza e vagas, dërshon me 4 pi të treta. 4 pi over 3, this is the K. Now that we have this K, we have to write down the complete expression where E would be a function of Z and time, because the wave is propagating along the Z-axis, and this is equal to AX, which is the polarization of the wave, or the direction of the electric field, times the amplitude, which is 10 to the power minus 4 volt per meter, times the cosine of 2 pi f time. This is omega t, right? Cosine omega t minus kz. Now, this is a good expression, but this, it might be best if we include also a phase difference. So let's add here some phase, and this phase, why do we need this? Now, imagine for a moment that t is equal to 0 and z is equal to 0. This means 0, 0, cosine 0 is equal to 1. So, if the wave is maximum at time t equal to 0 and z equal to 0, that means that the phi will be 0 also, okay? But here we notice that the wave is not maximum at z0, it's maximum at z equal to 1/8, okay? For this reason, we may have a phase difference. Let's call this one phi 0. Phi 0 is just is a constant which we add in order to adjust the initial conditions. Now, we have this expression for the electric field wave, and then we have to substitute. Wait a second, we have to figure out that at t equal to 0, so this one, let's check here. This is going to be cosine. If we put t equal to 0, this whole thing will be 0, minus kz, minus k is minus 4 pi over 3, minus kz, minus 4 pi over 3 times z, which is 1 over 8, okay, plus phi 0. This is equal to what? Is it equal to 1? This is equal to 1, and this is also equal to cosine 0, okay? Because we said that this whole thing, at this specific value, z1 over 8, it is this maximum, it's this point. So this cosine, we know is maximum at 1, so this is 0. Which means that this phi 0, so we have this whole term here, this is equal to 0. So we can say phi 0 is equal to, help me with this one, phi 0, this is 4 pi over 8, we get pi over 6. Okay, so this is so it looks like in this general expression, we just substitute this phase pi over 6, and now we are set, okay? So we found the complete solution, having the specific details. Now, the other question is to find, we can ask, in fact, what is the age? Okay, so that's the other essential question. And for this, I guess we have to, regarding this, first of all, we need to find the direction. And as we mentioned before, AX times AY, it should be equal to the direction of the propagation. So here we can directly report that H is going to have a direction along the AY times the magnitude, and the magnitude of magnetic field is always equal to the magnitude of electric field divided by the impedance. So for a moment, let's write here E0 over this impedance. Now, this impedance, we checked what it was, right? It was permeability over the permittivity. So you can correct me in this. So this eta, this was, I think it was the square root of mu over epsilon, okay? And then let's check what we get. we have here mu r, mu 0, over epsilon r, epsilon 0. This is all square root, and this is equal to mu r over epsilon r times mu 0 over epsilon 0. This was 120 pi, right? So this is equal to, this is 1 over 4 square root, so it's going to be 1 over 2. So this makes this 60 pi, okay? So here we have the 60 pi. So here we can write, instead of E0, this is going to be 10 to the power minus 4 divided by 60 pi. So this is the amplitude of h times cosine terms, okay? So this cosine that we have here, we just add it also here, which is going to be omega t minus kz plus pi over 6, okay? We got it. So this is the expression for the magnetic field component. Now, we got what the k was, and maybe we can simplify this part a little bit, or take it out. Another question is, find location Z find at which point of Z where E is equal to E max after 10 nanoseconds, okay? So after 10 nanoseconds, where we are going to get, let's say, the next maximum value for the electric field. Now, to answer this question, we look at this expression, and we have to substitute for t. What is 10 nanosecond? 10 nanosecond is equal to 10 times 10 to the power minus 9, which makes this equal to the 10 to the power minus 8 seconds, okay? And then we substitute these in this expression, and this is going to be, let's write it here. The amplitude is the same, 10 to the power minus 4. So here we have cosine of 2 pi f. So we have here 2 pi times frequency, it was 10 to the power 8, because this was 100 megahertz. Mega is 10 to the power 6 times 10 to the power 2. We get here 2 pi times 10 to the power 8 times time is 10 to the power minus 8 second, because 10 nanosecond, that's what it is. This is this is time t minus k is 4 pi over 3, 4 pi over 3 times z plus pi over 6, and this whole thing is expected to be a maximum, which means that this is going to be equal to the cosine 0, but it can also be cosine what is it, minus pi. So once we look at this, we can even call this one cosine 2n pi, okay? Because we know that cosine, it's 1 at 0, it's 1 at 2 pi, at 4 pi, at 6 pi. So probably a more general expression we can get it from here. So at this moment, we cancel this out. We have 2 pi plus pi over 6 is equal to what? So let's write it here. 2 pi plus pi over 6, let's get this plus pi over 6, minus 4 pi over 3z, this is equal to 2n pi, okay? So, in order to find z, so the question is find z to do this, let's factor out the pi. So let's write it like this. Actually, what we can do, we can cancel out pi's everywhere because it's pi everywhere. So I guess we can cancel these. So we are left with 2 plus 1 over 6 minus 2n. This is equal to 4/3 z. Okay. So apparently we found z. We just need to multiply everywhere with 3 over 4. And here we get 2 plus 1 over 6. That's 13 over 6. So this is 13 over 6 minus 2n. This is equal to z. But we multiply with 3 over 4. So we make this 6 over 4. 3 here. 24. So I guess here we have a series of possible values of z where the electric field would be a maximum after 10 nanoseconds. So in principle, after some time, we are asking to find these locations. So we're going to find this one, then sorry, we don't have much space here, this one, and so on. So what we learned here, we just saw an exercise of how, and maybe the most essential expression which we should take note is this omega times permeability times permittivity. Okay, so this was the propagation constant, this k, and this omega, this is related to the frequency in this way. And any other thing, anything else? No, this is going to be all of it. Okay. Do you have any question? So we also saw how where we need the impedance, where impedance in fact it's important here. So okay, I thank you. So this was, I think, this is all I wanted to cover for today. We just did a small review actually of how unbounded lossless medium, how they look like, and what is something which is relatively tricky for them. That's what we saw. And I guess tomorrow we have another session. So if you have, I can wait for a little more, a few seconds, if you have any more questions. So if you have a question, please just write in the comment section. If not, then we can close this for